In this lesson, we will acquire and validate our first measurement from an NI DAC device. In this section, we will explore the parts of a project. Consider a scenario where you're conducting experiments on the growth rates of plants in different environmental conditions. You need to collect and track data such as temperature changes, humidity, and soil acidity. Where would you begin creating an application to acquire this information? Data acquisition is the process of measuring an electrical or physical phenomenon with a computer, and you can do this by using NI DAC systems and LabVIEW NXG. A DAC system consists of a sensor, an NI DAC device, and a computer. You choose the sensors you need based on your application. Different sensors measure different phenomena. Depending on the type of sensor, its electrical output can be voltage, current, resistance, or another electrical attribute that varies over time. For example, to measure pH, you would use a pH probe connected to a DAC device that could read the voltage values that the pH probe produces. To measure temperature, you could use a thermocouple, which produces a voltage that varies based on temperature. NI DAC devices come in different form factors, from NI compact DAC systems to multifunction DAC boards, such as the X-Series DAC board. You select different NI DAC devices based on the complexity of your application and performance requirements. LabVIEW NXG running on a computer can acquire these signals from the DAC device, analyze them, and display the results. You can group real-world signals as either analog signals or digital signals. Analog signals are signals that vary continuously and have continuous values. Examples of analog signals are temperature or current. Digital signals are signals that transfer binary data, on and off, high and low. Analog input describes measuring an analog signal and transferring the measurement to a computer for analysis, display, or storage. Let's take a look at some examples of analog input. This analog input example acquires a value from a thermocouple sensor at a relatively slow rate of 2 samples per second. This analog input example acquires a high-frequency voltage signal at a much faster rate of 1,000 samples per second. Other analog input examples include acquiring signals from accelerometer sensors, strain gauge sensors, microphones, current signals, and more. Analog output describes generating analog signals from your computer and NI hardware. Let's take a look at some examples of analog output. This analog output example outputs a voltage ramp to control the speed of a fan. As the voltage increases, the fan speed increases. As the voltage decreases, the fan speed also decreases. Another analog output example would be to output a stimulus signal to a unit under test. For example, you might need to send a sine wave, square wave, or triangle wave with a specific amplitude and frequency to your unit under test to investigate how the unit under test responds. Digital input describes measuring a digital signal and transferring the measurement to a computer for analysis, display, or storage. Let's take a look at some examples of digital input. This digital input example reads the status of a physical button or device. For example, if the digital signal has a low voltage, that can mean that the physical button is not pressed. And if the digital signal has a high voltage, that can mean that the physical button is currently pressed down. This digital input example shows that your application could wait to receive a start trigger from an external digital signal before your application starts a task like acquiring data. This digital input example reads a digital protocol signal where a high voltage represents a binary 1 and a low voltage represents a binary 0. Digital output describes generating digital signals from your computer and NI hardware. Let's take a look at some examples of digital output. This digital output example outputs a digital signal to turn on an LED or another device. This digital output example outputs a trigger signal to trigger another device to do something. And this digital output example generates and sends a digital protocol signal. This course will use mostly analog input measurements for examples. In this section, we will talk about how to set up and connect NI DAC hardware. First, make sure you install LabVIEW NXG and the NI DAC MX driver. Then, refer to the user manual for your DAC device for detailed instructions on how to connect your NI DAC hardware to your computer. For example, I have the CDAC 9178 compact DAC device that contains multiple C-series modules, and I can connect it to my computer using a USB cable. Next, I need to connect my DAC device to the sensors and signals that I want to measure. In LabVIEW NXG, I can find guidance on this by viewing the pinout, manual, and specifications for my DAC device. Let's say I want to figure out how to connect a thermocouple sensor to my NI9213 thermocouple module, and a quarter bridge strain gauge to my NI9236 strain module inside my CDAC 9178 compact DAC chassis. To do this, click on your instrument in the System Designer. Now, I'll click on my 9213 thermocouple module, and now I can view the pinout diagram. Which tells me that the thermocouple connections go to TC positive and TC negative. So thermocouple channel 0 connects to these two terminals. Thermocouple channel 1 connects to these two terminals, and so on. So now I can make the physical connections. Now, I'll click on my NI9236 quarter bridge strain input module and view the pinout diagram, which tells me that strain channel 0 needs the excitation source connection here, analog input signal connection here, and quarter bridge completion connection here. Lastly, you can also view the manual and specifications for this device by clicking these buttons. In this section, we will walk through acquiring and generating signals from an NI DAC device and exploring and analyzing that data to validate the signal. The next step is to acquire signals. But before we acquire a signal, let's make sure that we understand the fundamentals of choosing the correct sampling rate for an analog input signal. Sample rate is the rate at which the DAC device acquires a sample on each channel. For example, this analog input channel is acquiring at a rate of 10 samples per second, or 10 Hz. Now, let's take a look at how to choose the correct sample rate based on the signal you are trying to acquire. Here, we see that the signal that we are trying to acquire is a sine wave that has a frequency of 100 Hz. This means that the sine shape repeats 1,000 times per second. If you set your NI DAC device's sample rate to 100 Hz, the same frequency as your actual signal, your acquired signal for this example will look like a straight line, which does not accurately represent the actual signal. If you set your NI DAC device's sample rate to greater than 2 times the actual signal's frequency, your acquired signal will accurately represent the actual signal's frequency. If you set your NI DAC device's sample rate to 10 times the actual signal's frequency, your acquired signal starts to accurately represent the actual signal's frequency and shape. The takeaway is this. You must sample at least greater than 2 times the maximum frequency component of your signal to accurately represent the frequency of your signal. And typically, you must sample at least 5 to 10 times greater than the maximum frequency component of your signal to accurately represent the shape of your signal. Now that we understand how to choose the correct sampling rate to acquire a signal, we will now acquire and visualize our signal using a measurement panel. From the System Designer, I can navigate to our DAC device. Here, I see my CDAC 9178 chassis, which is named CDAC1, and then I'm going to choose the voltage input module, which is named as CDAC1 Mod 8, since this module is in slot 8 of my chassis. Notice that I can give this module a more descriptive name here if I want, but I'll just leave the default name. To launch a measurement panel, I'm going to click this button. This will create a new project, and in the measurement panel, I can immediately start viewing live data. Right now, I'm viewing the data for the CDAQ1 Mod 8 module on channel AI0. This channel is currently connected to a light sensor. So as I cover the light sensor, the voltage decreases. And as I let more light shine on the light sensor, the voltage increases. It looks like I need to adjust the min and max of this measurement panel, so I can configure that over here in the Channel tab. For this sensor, the minimum should be 0 volts, and the maximum should be around 0.5 volts. Now I'm getting better resolution for the light sensor signal. The Channel tab is where I can configure channel and measurement-specific settings for my measurement panel. The Task tab is where I can configure timing information. For example, I can change the history duration to set how many seconds of data to show on the measurement panel. Right now, it is showing 5 seconds of data. Now, it's showing only 1 second of data. I'll change it back to 5 seconds. I can also set the sampling rate. Right now, the measurement panel is auto-managing the timing, and I set the sample rate to about 117 Hz. To manually set my own sampling rate, I can deselect this option and request my own sampling rate. If I set it to 1 Hz, notice that the measurement panel acquires 1 sample per second. If I set it to 4 Hz, it acquires 4 samples per second. Now, I'll set it to 1000 Hz, and it acquires 1000 samples per second. You can click this button to stop the acquisition. I can rename this measurement panel with a more meaningful name. And if I want, I can also save this measurement panel as a .task file. I can also save the project containing this task. Now, I will add another measurement panel for my thermocouple channel by going to the System Designer, selecting my thermocouple module, and clicking this button. In the Channel tab, I can configure the signal type to thermocouple. Select which channel, for example AI0 or AI3, and I can select the units and the minimum and maximum range that I expect for this channel, and also some thermocouple specific settings, such as thermocouple type and CJC source type. The Task tab allows me to set how many seconds of data to show on my measurement panel and my sample rate. Now, I will add another measurement panel for an analog output channel by going to the System Designer, selecting my voltage output module, and clicking this button. In the Channel tab, I can configure the signal type, voltage or current depending on what's supported by the module, select which channel, for example AO0 or AO1, and I can set the minimum and maximum range that I expect to output on this channel, and set whether to output a constant value or a sine wave. I'm going to leave this set as a constant voltage value. And here is where I can set which constant voltage value to output. To start actually updating the voltage that this analog output channel generates, I need to click the Run button. Now, this channel is outputting whatever voltage value here that I'm specifying. Now, I'll set my final update to 0 volts and then stop this measurement panel. Now, I will add another measurement panel for a digital output channel by going to the System Designer, selecting my digital output module, and clicking this button. In the Channel tab, I can select which channel, for example port 0, line 0, or port 0, line 1. Each line can output a high or low voltage, and a port is a collection of lines. And here is where I can set whether to output a high or low voltage. To start actually updating the output that this digital output channel generates, I need to click the Run button. Now this channel is outputting the high or low voltage that I'm specifying here. Now I will set my final update to a low voltage, and then stop this measurement panel. If you want to view additional channels in the same measurement panel, you can click the Create New button here. Select the channel, and configure it. If you want to add another channel with the same configuration, you can click the Duplicate button here. With multiple channels, it's often easier to view and update the configuration for all channels by using the table view here. When using multiple channels within the same measurement panel, the Task tab settings apply to all channels, so that means all channels will have the same sample rate. After you have finished and stopped acquiring data in an analog input measurement panel, you can examine the values. If you hover your cursor over the graph, you can view the values for one or multiple channels at that point in time. You can also zoom in on a section of your acquired data by making adjustments up here. You can also move these two cursors to points of interest and view the corresponding values of your channels in the tile view. If you need to further explore your acquired data to validate whether it is correct, you can capture the data from your measurement panel, then analyze your captured data using configurable analysis panels, and also export your data to file for more analysis. In this example, I'm acquiring voltage measurements from an accelerometer sensor attached to an unbalanced fan which is rotating at about 80 rotations per second. To validate that my acquired signal looks correct for this particular fan, I need to verify that the acquired signal contains specific frequencies, such as around 80 Hz, and 4 times that frequency at about 320 Hz, and 8 times that frequency at about 640 Hz. Since the highest expected frequency in my acquired signal is about 640 Hz, I need to make sure my sample rate is at least greater than 2 times that frequency. For this example, I have set my sample rate to 2.56 kHz, so it is 4 times greater. I will begin by capturing data from the measurement panel by right-clicking the data and selecting Capture Data. This saves the data as a data item in the Capture Data tab, and I can rename the captured data with a more descriptive name. I can select File, Save All to include this captured data item as part of my project. This is a convenient way of saving interesting data for future use. To open and explore the data in a captured data item, double-click it. In this example, I cannot verify that this signal contains my expected frequencies just by looking at this graph, so I need to do some further analysis. To do this, I can use an analysis panel on my captured data. The interactive analysis section contains a variety of analysis panels, such as amplitude measurements, statistics, filters, FFTs, and more. For this example, I will use a tone measurements analysis panel. The configuration pane is where I can configure the analysis panel settings, so I will configure this one to search for multiple tones and set a minimum threshold for a tone. I can now look at this frequency domain graph where the y-axis is amplitude and the x-axis is frequency in hertz, and I can analyze which frequencies are in my acquired data. I can see my expected frequency of about 80 Hz here, and 4 times that frequency here, and 8 times that frequency over here. So now I've validated that my acquired data looks correct. Notice that I can capture data from my analysis panel too. I can also export my captured data to a comma-separated or CSV file by right-clicking a captured data item and selecting Export. This allows me to share this data with other programs and continue analyzing the data. In this section, we will discuss some tips to help troubleshoot if you get unexpected I/O results from an NI DAC device. If you see unexpected input and output results, or I/O results, from your DAC device, then try checking the following.